All right, next up, passwords. Now, the password topic is a huge one, but a beautiful one. So let's see, how would you go about breaking a password? What would you do? Now, the first one that might come into mind is an online brute force. It's called online because we're interacting directly with the authentication server, and it's brute force because we're basically attempting to send every possible password combination, hoping that we're going to hit the right one. Now, this is not going to work. First of all, it might take you longer than the rest of your life, and secondly, it's extremely noisy. Everybody can detect this attempt. Alright, so you're gonna think, let's make this more efficient. Why not just hack the server and just steal all the passwords in there? Well, that's also not going to work because in most cases, if not in all situations, passwords are not stored in clear text in any Linux, Windows environment or in any web application, or they should not be stored in clear text. And that's because passwords are not stored in clear text but as hashes. Now, a hash is the result of a mathematical operation that takes any kind of input and produces a fixed length output, preferably unique for each type of input that was provided. So think of the hash as some sort of a fingerprint of that input data. And very importantly, this is one way. We can only hash the original data into the resulting fingerprint. We can never obtain the original data back from that fingerprint. So generally, the process of obtaining these hashes from an authentication server and attempting them to crack them on your own time, on your own machine, this is considered to be an offline attack. You just grab what you need and then go home and do your homework. That's offline attack. Trying to crack those hashes and figure out which passwords were originally used to generate them. And of course, we do need to mention this comic here as well, because, well, social engineering is going to beat any cybersecurity attempt, any penetration attempt every single time, no matter how technologically advanced it is. The human link is the weakest link. So when trying to breach a system, when trying to breach security, you're going to have the most chances with a social engineering attempt. But that's not exactly our focus this very moment. So coming back here to our first method, the first one was brute force, which is basically just a way of attempting as many password combinations as we can. Now, this is going to be really difficult to perform on a live system. So as an online kind of attack, this is probably not going to work. Well, simply because it's going to take you a very, very long time. And of course, you could do this manually if you want. You could try, attempting password 1, password 1, 2, password 1, 2, 3, and then keep going until you realize that this is not the best approach. So we're going to have some automated tools that can do this for us. Some example here would be, for example, Medusa. We can use Medusa to brute force into specific services. We can load specific modules right here with the -m parameter for FTP, SSH, HTTP, whatever type of service we want to crack, and then specify the list of target IP addresses, target usernames, and target passwords to test. So we can either use predefined lists of usernames and passwords, or we can use Medusa to perform brute force attempts using full char sets. For example, all the alphabet letters, all the numbers, or the punctuation characters, and so on, for passwords at least. Another one is Hydra, which can also be used to brute force into a number of services. It can also provide the list of login usernames, potential passwords, and you can also see here the supported services. And I'm sure you're going to recognize at least a few here. For example, HTTP, GET or POST, SSH, SNMP, SMTP, Windows SMB, MySQL, and so on and so forth. It's just a simple example here at the bottom, how easy it is to use Hydra with a predefined user list and a potential password list here, try to crack into this FTP server. And another one is John the Ripper, also called just John, that's it. Brute force utility for password cracking. And finally, a very powerful tool is Hashcat. Also for password cracking, if we want to know more about Hashcat, we're going to have to open the manual page. And among all the parameters here, we're going to find some interesting stuff like the char sets or the character sets that it can use for pure brute force, or the attack mode. Now, straight is going to use a simple list of potential passwords that you can provide. Combination is going to mix and match brute force with that specific list, that dictionary list. Pure brute force And you're also going to see the types of hash supported, and this list is absolutely huge. So you can see it starts with MD5, SHA-1, you can probably recognize a couple of here, NTLM for Windows hashes, SHA-256, SHA-512, and so on and so forth. Cisco, PIX ASA, WPA, WPA2 for Wi-Fi, even Android pins. So it does support quite a wide array of hashes that you can choose from. And generally, as you can see from most of the options in these utilities, they support two approaches. One of them is by using char sets, that's character sets. You're simply iterating through the entire alphabet and then all the combinations between alphabet letters and numbers and punctuation signs and spaces and so on. Now, the other approach is by using a word list, also called a dictionary. That's because most passwords, at least those that are generated by humans, will be built by using some sort of a dictionary word. If it's, I don't know, maybe it's a birthplace, a person's name, a pet's name, it might be a superhero's name. It might be something that can be found as a legitimate word in a dictionary. Now, normally we're going to have a hybrid approach where we try to crack passwords by combining these dictionary entries with char sets combinations, so that we can also find passwords like Superman 123 or New York 86. Now, examples like that. But the more complex the approach, the more time is going to take you to break that password. Simply because you're going to have so many combinations to try. And if you're doing this as an online attack, as in you're interacting directly with the authentication service, it's probably not going to work, also because you're going to have a huge delay in each authentication attempt. So think about it. For example, if you log into Gmail or into Facebook and you input your password wrong, how quickly do you receive the response that your password is wrong? It's pretty fast, but it's not instantaneous. It's still going to take you like 1 second. Well, 1 second is huge when you need to try 1 trillion password variants or password combinations. So it's simply not feasible. Now, the second reason why this is not going to work is because, as I said before, this approach is very noisy. It can easily be detected by any kind of application, any type of authentication server. Anything can detect a high number of failed login attempts from the same user, from the same IP address in a short time span. This is a big indicator of a brute force attempt. If it's not detected by the application, it's going to be detected by the firewall or by some IPS device. It's most likely not going to be feasible in real life anyway. And if you get detected doing this, there are kind of two approaches that most applications take. One of them is by implementing a backoff. Try to mistype your phone's PIN a couple of times in a row, right? Just type something random in there. Now you're going to see that after a couple of attempts, the phone is going to tell you back off for a couple of seconds. You can try again in 10 seconds. If you fail again, you're going to have to try again in 30 seconds. If you fail again, you'll have to wait 5 minutes or more. This is exactly designed to thwart these brute force attempts. Now, in a more public environment, for example, a public login page on a website, this might also translate into a permanent or temporary ban on your account. If you failed your login too many times in a row, you might get your account blocked. So you might need some admin to intervene and unlock your account before you can try again. Again, this is not going to work for a brute force attempt. So we talked about hashes a number of times already. Let's just make sure that everybody here is on the same page. Now, a hash is just a mathematical operation that transforms any set of data as an input to a fixed length, unique output string. Let me show you how this works. Now, hashing algorithms are public and well known, which kind of means that you don't really have to implement anything. You just have to use them as they are. They're standardized. And you can access them online. You can find command line utilities, small utilities on Windows or Linux that can calculate these hashes for you. You can just start online and search for hash calculator. That's it. All right. Doesn't matter which one you choose here. Let me just find a random one here, like, I don't know, onlinemd5.com. You can pick whichever you want. If we scroll down here, there's a hash generator for text. All right, we have MD5 selected as the hashing algorithm, which stands for message digest 5, by the way. And you can see here that we can provide any kind of input as text. So if I just type, I don't know, 1, that's it. That's going to be the resulting hash of number 1. Pretty weird, right? I mean, how did you get this from 1? Now, if I type 2, that's going to be a completely different type of hash. Now, if I type, for example, password in here, that's going to be a different type of hash. If I type password 1, the hash changes entirely. If I change password 1 to password 2, again, the hash is going to change entirely. And it doesn't even matter what kind of input I have in here. I mean, I could just, I don't know, go ahead and copy the first paragraphs of, the Tesla article from, from Wikipedia and just paste it in here. My hash is still going to be calculated, and it's always going to be the exact same length. And it also should be unique. That is, changing one single character in this text should provide me with a completely different hash value. Now, another website that I can use to compare different types of hashes is this one right here. So let's add a password 123, all right, as a hash string. Let's calculate this. And at the bottom of the page, you're going to see pretty much all the hashing algorithms that we are using nowadays. Some of them have been deprecated, of course, because they're old and considered not so secure anymore. But you can find MD5 in here, which is 16 bytes in length, which is a 128 bits, right? That's the MD5 hash value in here. SHA-1, which is 160 bits, a bit larger. SHA-256, which is, I'm gonna let you guess how many bits that is. SHA-384, 512, and so on and so forth. You can see that there are a bunch of hashing algorithms available nowadays. That's a very quick way of generating a valid hash from a text input or from a file. You can see you can also upload files in here as well. It doesn't matter what kind of input you provide. You can just provide a string input. You can upload a 4 GB ISO file. It's still going to return a hash output of the same fixed length. I mean, you can even do it on the command line if you want. So, for example, let's say if I want to echo Iron Man. So let's say that's the password that I'm going to use, and then pipe this to something like MD5 sum, right? You can see it right here. We have MD5 sum. The same, we're going to have access to utilities that calculate SHA. So have SHA-1, SHA-512, 256, and so on, right? So if you just pipe this to MD5 sum, that's going to be the MD5 hash that you get from Iron Man. Now, one gotcha here, one caveat. If you are generating hashes like this, keep in mind that the echo command also adds a new line at the very end. So whenever you just echo Iron Man on the screen, you're going to see that the output jumps to the next line and you get the Linux prompt again. Well, that's because it's not exactly just Iron Man, it's Iron Man plus the new line character at the end, and that character also gets hashed. So if you want to skip that character and just hash the actual letters that you're seeing on the screen, add a -n to the echo command. Now, if you output this, you're going to see that the hash actually changes, right? So there are different values here because between this Iron Man and this one here, there's one extra character, which is the new line character. So careful with this in the command line if you want to prepare your scripts, for example, for your calculating hashes. If you check the manual page for echo, you're going to see that the first option here is do not output the trailing new line. So that's exactly what we did right here. Also, one thing that's mandatory for a good hashing algorithm is that it's supposed to be irreversible. So there should be no way of determining the original text or the original content from the hash value, which is also why we use them to store passwords. So we never store passwords in clear text. We hash the password, we store the hash, and whenever the user comes in and wants to authenticate, we recalculate the hash of whatever password they're providing, and then we compare it with the one that we've stored. So we're just comparing hashes, we're never comparing passwords. And this is also great because nobody can have access to a user's password, not even the admin or the root user, because they are simply not visible, they're not there. The password is never stored in clear text, or shouldn't be stored in clear text, regardless if we're talking about operating systems or web applications or any type of web application. You're never supposed to store a user's password in clear text. So basically, this brings us to the problem of what does cracking a password actually mean? Since we cannot find the actual password stored on that server, then cracking a password basically means finding the original string that generated the hash that is stored on that server. Now, we also have to address the problem of hashing collisions. And think about it this way. So an MD5 hash has 128 bits. How many possible combinations can you have with 128 bits? Spoiler alert, a lot. But think about it from the other side, or on the input side. if you're providing any kind of input that produces a 128 bits output, let's say you're providing a 1 gigabyte file as an input, 1 terabyte file as an input, how many bit combinations are possible with a 1 terabyte file? Well, again, a lot, but much, much more than the possible combinations in the hash. So which brings us to the problem of how likely it is that we could find two different inputs that can produce the same hash output. And the answer is sometimes quite likely. Simply because we have so much potential input that has to fall into a unique 128 bits of value. There's always going to be, for each hashing algorithm, at least two kinds of input at some point that will produce the same hash output. And that's what we call a hash collision. Two different inputs producing the same hash output. Now, why is this relevant? Well, think about the fact that we're using these hashes to store passwords. Well, what if we can find alternative input that produces the same hash output? Can that input be used as a valid password? Yes, the answer is yes. Because the system doesn't look at the password, only look at the resulting hash. So if the hashes match, it's okay from the system's perspective. You are providing a valid password. And actually, this is something that has been studied before in statistics, as it's called a birthday paradox. And the problem kind of says like this: how many people do you need to have in a single room in order to have a 50% chance of any two of them sharing the same birthday? How many do you think? And, you know, many people would think about, well, 365 days in a year, maybe, I don't know, 50% chance, maybe half of that, maybe 180 or something like that. Well, no, the answer is just 23. The trick here is that we don't need two of them to have a specific same birthday, but we need them to have any birthday as long as they both share it. If you increase this, actually, if you go up to 30 people, the chances grow tremendously, up to 70%. If you go up to 70 people, it's almost 100% confidence. And that's exactly what happens with hash collisions as well. Basically, the more hashes you can try, the better chances you have to find such a hash collision. And actually, the bad news here is that you don't even have to try that much, right? Because your chances grow quite fast. And that's exactly the reason why many of the hashing algorithms that you've seen on the previous webpage have now been deprecated, because they have been proven to be very vulnerable to birthday attacks like this, or collision attacks, which make them completely unsafe for storing sensitive information or for hashing sensitive information like passwords. So for example, if we were to rely on finding hash collisions, you know, maybe my password, which is password123, is going to generate this MD5 hash right here. I'm going to store this hash. But who's to say that if I use the I really like cheeseburgers with barbecue sauce password is not going to generate the exact same hash value? Or even better, I don't know, maybe the first episode of The Mandalorian is going to generate the same hash output as my password123 input. Right? They are all potentially valid passwords. Now, if you're able to upload The Mandalorian within a password field, that's going to be some tremendously awful input validation on that website. So probably that's not going to be one option, but you get the idea here, and you get the potential repercussions of hash collisions. And since we're talking about files, the problem with hash collisions is not necessarily restricted to storing passwords. Because in many situations, cybersecurity tools like antivirus, anti-malware, advanced intelligence software that looks at file behavior on your machine and scans those files is going to rely on file hashes. So many enterprise solutions actually don't scan your files at all. They just hash those files and then use an online reputation service to search that hash value and see whether it matches a malicious file, or if it has been scanned before and has been validated that it's okay, it's not malicious. Now, having hash collisions in a security environment like this could potentially allow an attacker to upload and execute their own malicious code by crafting a malicious file that matches, through a hash collision, a well-known good reputation file. Now, we've seen in a previous demo with the Kane password cracking how long computing hashes in order to break passwords can actually take. Now, fortunately or unfortunately, depending on the side that you're on, we do have a better solution for this, and that one is called rainbow tables. Now, rainbow table is just a file with pre-computed hashes for all possible character combinations that can be used as passwords, pre-calculated and stored in a sort of a database. The idea behind a rainbow table is that we're shifting the computing effort from calculating hashes to searching into a huge database. And they can actually be huge. I mean, we're talking about hundreds of gigabytes in size, if not even terabytes, that store all the possible password combinations calculated with a single hash algorithm. So yeah, of course, you're gonna need different rainbow tables for different hashing algorithms. Of course, somebody has to create these tables beforehand, so somebody has to dedicate a huge amount of processing power into building such tables so that you later on can just quickly search through these databases. Now, you have the options of downloading these tables if they have been previously generated by somebody else, or you can just generate them on your own machine. Now, there are a few places online where you can just download these rainbow tables for free. This is one of those websites. So for example, you can download NTLM hashes, SHA-1 hashes, MD5, LAN manager. Now, probably not going to need this anymore, but you can see that even for MD5, which is a quite short hash, just 128 bits long, the entire data set here is 4.3 terabytes in size. You can basically choose now which type of rainbow table you're going to have. So for example, if you're only interested in lowercase alphabet letters ranging from 1 character to 10, so this one here, you can use it to crack MD5 passwords that only use alphabet letters lowercase and they're at most 10 characters. You can see that these are 179 gigabytes in size. Going further here, mix alpha, that's going to be lower and uppercase, combined with digits, at most 9 characters. That's going to be around 1 terabyte. That's a rainbow table right there. Of course, if you try to mix them up even more, so for example, if you add symbols as well as spaces, ranging up to 8 characters, this time it's still going to be 1 terabyte in size. So they grow exponentially here. The more complexity you add to the character sets that can be used inside of a password, the larger the rainbow tables are going to be. Now, these can be downloaded for free, but you can also buy rainbow tables. I mean, if you think about how long it would take you to generate these rainbow tables, buying them at some point might start making some sense. And as you can see, they're not cheap by far. So as you can see, rainbow tables can be quite dangerous from a cybersecurity perspective, simply because instead of, cracking a password and waiting days, months, or even years, and using a huge computational power to do so, you can just search a database like this, and it's only going to take you like a couple of seconds or minutes at most, and you're going to find the exact password combination that generates that specific hash. You're basically searching for a hash. That's it. So how do you mitigate this? How do you fight against this? Now, I would say that the first option would be to use very long passwords or passphrases, like entire sentences, so that there won't be any possible rainbow table that can be generated for a password of 30 characters in length. That's simply going to be computationally impossible. But even so, that's not going to be enough, because you still risk running into hash collisions. So even though your original password might have been 30 or 50 characters in length, nobody can guarantee you that there isn't a 5-character password that can generate the exact same hash, which might be available in some rainbow table out there. So how do you stop this? Well, the process is called password salting. And this salting here actually means that instead of just taking the password and calculating an MD5 hash of that password, we're now taking the password and then adding something extra at the end. Like a simple suffix, just a few bytes, a few characters at the end or at the beginning, doesn't matter. And then we calculate the entire MD5 hash of that resulting string. That is the hash that we are going to store in our user database. And you're going to ask, well, how does this help me? I'm still storing a hash. I can still crack that hash, right? Not exactly, because what you're providing is just the password. The salt is stored on the server, which means that if you're using a rainbow table that is going to provide you with a valid password that can be used to generate the hash stored on the server, well, that valid password is not going to be valid, because it's supposed to be concatenated with the salt, with the extra suffix, whenever it is sent to the MD5 algorithm. So let's see what happens with rainbow tables and hashing. Let's assume that we have a user here and their password is secret password. Now they try to authenticate. So they're going to send this password to some hashing algorithm from the authentication server. And the hashing algorithm is going to combine their password with a salt. In our case, I'm going to assume that the salt is 1234. So the resulting MD5 hash, let's say, is going to be something like this. And this is what's going to be stored in the database. Now, assuming that an attacker comes in and tries to look up this hash in a rainbow table, it might actually get lucky and find that they have a match for secret password 1234, because that's the exact string that was used to generate that hash. Now, when the attacker tries to use the secret password 1234 as a login password, this of course is going to end up in the same login mechanism, the same hashing algorithm, which is going to be combined with the salt again. And of course, the result is going to be different, because the text that we're hashing is going to be now secret password 1234 1234, and of course it's going to generate a different type of hash. Authentication is going to fail. So password salting defeats rainbow tables simply because it would theoretically require you to have a rainbow table for each possible salt combination, which is not feasible, impossible to do. Now, this salting behavior is present in most operating systems by default. For example, on Linux, we can have a look inside the etc shadow file, which is going to store the password hashes for the users on our system. And right here is you're going to see the actual hash of my password, which has a couple of delimiters here. The first one being the algorithm that is being used, and the second one here, this one is the salt. So the salt doesn't have to be secret, can be stored on the same machine as the password. It can even be stored in clear text. It's not some sensitive piece of information. It's simply there to make the use of rainbow tables, well, unusable. Okay, so I've shown you how to download rainbow tables. Let me show you how to generate them on your own. RTGen stands for Rainbow Table Generator. It's a small utility that's very powerful. You can see how many hash algorithms are currently implemented. So we have LM hashes, NTLM, MD5, SHA hashes, and so on. At the bottom, you can see an example here, RTGen, MD5, specify what type of character set we're going to use, low or alpha, for example. What's the minimum number of characters in the potential passwords? What the maximum number? That's going to be between 1 and 7 right here. The rest of the values here, these are the table index, the chain length, the chain number. These are all parameters that specify how big the resulting tables are going to be. And finally, the last one is a part index, just in case, you're generating tables so big that they become unmanageable on the file system. All right, so we can try to generate one on our own here. So RTGen MD5, lower alphabet between 1 and 3 characters. I know that's not much, but I'm using at most 3 characters so that you can see this in real time and not wait for it. All right, so let's start this. Probably going to take just a couple of seconds here. You can see the plain text range. That's going to be between 1 and 3 characters, and the char set data is this one right here. That's just the alphabet, lowercase. Right, we have 65,000 of 100 generated, so we're done in about 16 seconds here, 17 seconds. Let's see what the tables were generated. And by default, that's going to be under user share rainbow crack. And there it is. That's the file that we just generated here. MD5 lower alpha between 1 and 3 characters, 1.6 megabytes in size. Not too much, but we did get it in just a couple of seconds. Now, there's one thing we should still do before being able to use this table, because we need to be able to search through rainbow tables as fast as possible. So there is also a sort operation that we can perform, RT sort, and we're going to perform it in the exact same location as our rainbow table. All right, sorted, done. Now let's see how we can use this rainbow table to crack a simple password, just a 3-character password. First, let's generate a valid MD5 hash for a 3-character password, just like that. All right, that's going to be our MD5 hash that we need to crack. One more step here. Let's call our crack and provide rainbow table location, and then the -age argument, which is going to include this exact same hash. All right. What do we have here? Result, this hash right here corresponds to the password XYZ. Of course, this was really fast here. We only have a small rainbow table, but you can see that we actually got it in under 1 second. It's just 3 characters, but it's a very good starting point. If you want, generate your rainbow tables, make them big, make them ready to crack more complex passwords, but be aware of the fact that it's going to take a very, very long time. All right, so I'm going to show you here how to crack a password using an utility called Hashcat from a known hash value. And I'm going to be using a word list. They come embedded in most security-oriented operating systems out there, even in some general Linux distributions. One of them is this raw.qtxt file in my Parrot security operating system that I'm running here in a virtual machine. And you can see it has a bunch of commonly, possibly used passwords that you can just take from this file and use in a brute force attempt. Now, this file right here is quite big actually. It's 134 megabytes in size of pure text and password combinations, which is not bad. Okay, so let's create some MD5 hashes. Let's assume that one password here is Superman. We're going to pipe this through MD5 sum, right? So that's exactly the result that we're going to get. Now, in order to just get rid of this trailing spaces and the dash at the end, we can also pipe this to the tr utility and make sure that we're eliminating the last part. All right, so we only have the MD5 hash right now. Let's get this and redirect this into a hashes.txt file. All right, now let's generate some more. All right, grab this. Go to a text editor, paste it in here. Let's multiply this a bunch of times in here and add some more passwords. So for example, Mario, pizza, password 1, password 123, QWERTY. And let's give it a more difficult one, like pass W0 or all right. So these are the commands that we'll be storing inside hashes.txt. Let's paste these back in our terminal and execute them. All right, let's have a look inside hashes.txt. There we have them. These are our hashes that we're supposed to crack right now. Okay, now I'm going to use the manual of Hashcat and to find exactly what we need here. So let's go down here. Right, so that's attack mode. We're going to use 0 for straight attack, that is just use the word list that I'm going to provide, and also the hash type, right? Remember we used MD5, so I'm going to use the hash type of 0. Let's exit this and use Hashcat as follows. Right, so we selected the MD5 algorithm, the attack type as direct, as using a word list. Let's save the output in a passwords.txt file. I'm going to provide the file with the hashes as well and the location of the word list. Rock you. Right, so let's see how this works. Right, give it a couple of seconds here to initialize. Now, normally this would work much better, by the way, if you were using a dedicated GPU, like an AMD or an NVIDIA GPU for this, because it's basically the exact same of operations that we're doing when we're crypto mining, right? Calculating hashes. Okay, so the status here is exhausted. Nobody's exhausted here, but we did exhaust the entire word list, which also means that we did not manage to recover all the passwords. We did recover 5 out of 7 though. Not bad, right? At least for, I don't know, an effort of 4 seconds. Not bad at all, actually. So let's have a look what this software did. Let's have a look inside password.txt. All right, sudo password.txt. So apparently it was able to crack Superman, password 123, Mario, password 1, and pizza. It did not crack QWERTY, which was actually a typo on my behalf, so this is my bad here. This is supposed to be QWERTY, and it did not crack passwords written like this either. That's simply because these are not dictionary words, cannot be found inside of a dictionary. But as long as it is part of a dictionary, now you can see just how easy and how quick we can crack a password like this. Actually, multiple passwords. Now, we weren't looking for one. We did crack 5 out of 7. So, good news, right? And you know what? Since we did not manage to crack those 2 passwords using a word list, let's try cracking them through pure brute force, right? Let's see how this works. First, let's get the hash for this weird password right here, QWWERT. And that one was second to last. So this one right here, let's copy this hash and try Hashcat now in brute force pattern mode. Now, if we look inside the manual of Hashcat one more time, we're going to find that we have some built-in character sets. So if you're just looking for alphabet letters, this is going to be the pattern that we're going to be using for each letter. Let's see how this works. Okay, so we have the same Hashcat command here with the same MD5 algorithm, but this time the attack is going to be of type pattern. This is the hash that we're trying to crack, and then we need to specify the actual pattern. Remember that $L meant an alphabet letter. So our password here is 6 characters in length, so let's add 6 characters for the pattern in here. Well, what do you know? We just cracked it in 1 second here with this pattern here up to 6 characters, and you can see here that the hash corresponds to our exact password, QWWERTU, typos and all. All right, let's try doing the same thing, but this time on our more advanced password, right? We're going to use this hash, right? So let's grab the last hash, the last one which we did not manage to crack. Have a look inside the manual page for Hashcat for the right pattern. So there it is. Now you're basically going to have to use pretty much everything in here, right? Lowercase, uppercase, numbers, and characters. So I'm going to use this question mark A, which combines all the above, right? So question mark A, that's going to be our pattern. Let's update our hashcat command, paste our last hash in here, and then update the pattern. PASSWORD. Let's see how this goes. Okay, so it does give us the ability to quit, create a checkpoint, pause, resume later, or check the status. Now let's check the status here. All right, so what do you have here? That's the current speed at which we are checking our hashes, and time estimated here is 2 years and 245 days. All right, so thanks for watching. See you back in 2024 with the results. No, I'm just kidding, of course, but it does take quite a while. So you can see the more complex the password is, the longer the password is, the time needed to crack it is going to grow exponentially. Now you're going to get better results on a graphics card, but you're still going to be looking for a complex password into the range of months, years, if not even more. All right, let's see one more type of attack. And this one is called horizontal brute force. And this one is interesting because it approaches the problem of password breaking from a different perspective. And the main idea here is that instead of choosing one user account and trying to break the password for that user account, why not choose a password first, like a common password, password 123, and then choose whether we can find a valid username that actually uses that password. Very useful approach when you can determine, or when you know, the exact naming conventions for the usernames inside of an organization. For example, just by looking at your email, you can probably determine if it's going to be like first name dot last name or something like that. If you can figure out how is the naming convention designed within that company, then you basically, just by looking at LinkedIn or looking at the official company website, you can determine how all the usernames are going to look like. Then, well, if you have 2,000, 3,000 employees and you know all their usernames, let's see if any of them uses password 123. So it's a reverse approach to password cracking. We first choose a password and then find a matching username. And what we just described here is called password spraying. Now, the second type of horizontal brute force is going to be credential stuffing. This one relies on the fact that perhaps at some point you've determined or you've managed to crack one password for one specific username. And you know that you have a user password combination that is valid on one website, on one service. Well, what if that same combination is valid for other services as well, or for other websites? People reuse passwords all the time. Why not try that? So this one is credential stuffing. It's kind of a brute force where you choose one username and one password and you try multiple services, just to see if that person has reused the same user and password combination on a different website. Now, this really was a pretty huge chapter. Congratulations if you made it this far. So for the exam, make sure you understand everything we talked about password attacks, starting with brute force and methods of performing brute force. Understand hashing. That's really, really important to understand what's going on, how those hashes are calculated, what are they good for, and especially the fact that they should not be reversible. Also, regarding hashes, make sure you understand the implications of related attacks like collision attacks, birthday attacks, rainbow tables, how are they built, what are they used for, and also how are they mitigated. Specifically, know what password salting is and how it's supposed to be done. So thank you for watching. If you found this informative and useful, make sure you like and subscribe, because that's all I need to keep this channel going, right? That's all the support that I need. Thank you so much for watching, and good luck until next time.